What are the two things? And actually, they're coming up on the next slide in the form of laws. Some guys wrote these laws. So what happens with regard to intensity with increasing temperature? Yeah, it goes up because the line's going up. That means they're brighter and brighter at these hotter temperatures. What's the other thing with regard to temperature? Remember, I kind of said if you see a blue star, if you see a red star, which one's hotter?
Blue.
Blue. Why?
It's on the
Yes, it's on electromagnetic spectrum. Blue is a shorter wavelength than red. Yep. Here's our Roy G. Biv, going backwards. Roy, oops, is this gonna work? Huh, doesn't want to. That's weird. Yep, red, orange, yellow, kind of in there. Green, blue, indigo. Now, if you're like me, I never like, oh, what color would you like? Indigo, violet. It's said, and I'm not sure if it's true or not, but that gives us 7 colors. And it's said that, who would have been Newton? Newton, not Einstein. But Newton, when he separated the colors of the rainbow, he wanted 7. And so he stuck in, I think, indigo. So anyway. Very good. So those two things, Wien's law, the W is pronounced as a V, it's German, was the one where you said the hotter the object, the shorter the length of the dominant wavelength. The shorter the wavelength. Okay, so that's what you guys told me, that the blue stars are hotter, shorter wavelength. Red stars are cooler. That's Wien's law. One of the things, and I could kind of go back to the slide we were just looking at, but did you see where it's not just in visible light, but it's in all sorts of different wavelengths that these objects, black body objects, are emitting their black body radiation. Okay, shorter than visible light would be what, the infrared and going to X-rays and the gamma rays. Longer than red would be infrared, and then radio or micro than radio. So that's Wien's law. Stefan Boltzmann's law was the other one that you told me, and it has to do with intensity. Basically, the hotter the object, the brighter it will be with regard to how much energy it's emitting. Now, one thing, if I do this, what's this? That's my wavelength. Yeah, exactly. And light definitely has this wavelength property, or has this wave property. And there are different types of waves. There are the longitudinal, the kind of compress, sounds like that. And then there are the, I think it's called transverse, where it goes up and down, and lights like that. That's why I remember the other day I said you can actually have picket fences. If they're crossing each other, then no light gets through. It's like, oh gosh. The other thing about light is that, and not just visible light, but all of the cousins, all the electromagnetic radiation energies, they also travel not only like this, but they travel in little packets called photons. Little packets called photons. Now, photons are, the way I think of it, kind of where the energy is balled up. What has more energy, if radiation is X-rays or if radiation is radio? X-rays, yep. Shorter wavelength, what's the frequency? Is it high or low? High, short wavelength, high frequency, perfect. The photons, here's where kind of when I think of, well, a little bit of both these laws. The photons, the little packets of energy that are all traveling at the same speed of light, actually, those photons have more energy. When I say those would be X-ray photons, have more energy than your, whatever I said, radio photons. So that's one more thing. So we've never really visited a star, okay? The most we've done are the Voyager missions, which, this is our sun, right? And our sun has a, remember what, and we're gonna talk more about the sun later, but what's this? What's that? Solar wind. Our sun has solar wind, yep. And so the solar wind collectively kind of peters out, and beyond the, let's see, we have the, what's this, the, after Pluto, it starts with letter K. Kuiper Belt, very good. And then it starts with letter O, what's this? Oort cloud, perfect, yep. So I understand even beyond the Oort cloud, the solar wind is kind of petering out. It's 2 months, okay? but it creates a big old bubble we call the heliosphere. The heliosphere, isn't that awesome? But anyway, I mentioned that because the Voyager missions, which were launched, I want to say in the 70s, they got some great pictures of the planets as they went by. And Voyager missions are, and this was a Carl Sagan idea, actually the little Voyager spacecraft, they knew that they were going to hopefully leave the solar system one day. And so they put on things like a message in a bottle. Like, if you find me, little alien, this is where I came from. Is that not adorable or what? And there's a little gold record in there and a kind of instructions how to make the record player. You might be like, how would they know how to communicate with alien life? Well, it's through, I think it might have been binary or map or something, little pictures. So I mentioned all this, I'm getting sidetracked, but these spacecraft are leaving the heliosphere, okay? So the heliosphere is the bubble around our star. Okay. Do you guys remember where the closest star is? How far away it is? About 4 light years, yep, about 4 light years. I'm telling you, there's a lot of space between the end of our heliosphere and the next star. I mentioned this in case you guys are aspiring to visit a star one day. It's not happening. Okay? So there are ways away. So, and then I go back to this idea of we got to be smart here on Earth. If we want to understand our neighbor stars, let alone our neighbor stars in our stars in our galaxy, let alone other galaxies, we have to tune our dial to look at different wavelengths. So anyway, so we can, just by eyeballing it, just us is not necessarily being astrophysicists, can look at a red star, you say cool, blue star, you say hot. Okay? So anyway. So I kind of inserted this. This seems a little out of order. I think we already talked about this, the 3 temperature scales. If you want to see how cold it's going to be or how warm it's going to be, you're probably going to go with Fahrenheit. And Fahrenheit and Celsius have a relationship of 1.8 and offset by 32 units. So, but the best thing we can do, especially in astronomy, is to talk in terms of units of Kelvin. Like the slide we started out with, you guys told me those were Kelvin temperatures. And those are actually potential temperatures of stars. Now, when we say how hot is this, what is the temperature of a star, we can talk about a couple different temperatures, but we're now talking about surface temperature. And absolute zero, all molecular motion stops on a Kelvin scale. 0 Kelvin is absolute zero. Okay, and they're offset by 273 degrees. Our star is about, the surface of our sun is about 6,000 Kelvin, 5,800 Kelvin. Okay. So yeah, back to what Newton did, and he gave it 7 colors, the Roy G. Biv. Can you guys see Roy G. Biv over here? Let's see if everything right. The battery died or something. Yep, it doesn't want to write. Okay. But, so here we have the longest wavelength, and here we have the shortest wavelength. I mentioned it the other day, and I won't, and you probably didn't write down, but it's called refraction. Refraction means bending. Can you see where this light has this trajectory? This medium is air, this medium is glass, okay? So as this light enters the glass, it's actually different medium and it changes speeds. And I kind of said that's why your diamonds look so pretty, because actually light is being refracted, bent. The thing about a prism is that it is selective so that, which one's bent more? Can you tell? Is it the red or the violet? Which one looks like it's bent more? To me, it kind of looks like the violet is bent more and the red's bent less. Okay, so the amount of kind of changing its direction, the amount of bending is related to the wavelength of the light. So this was how we can actually break white light out into its components. What does NM stand for?
Nanometers.
Nanometers, yep. I always think of Mork from Orc or something. Yeah, nanometers. Cool. So this could be like our, this is our cousins. This is our electromagnetic radiation, all of them. So over here at the shortest we had cosmic, didn't we? Cosmic, gamma, X-rays, then ultraviolet. One of the things I like about kind of putting visible light in order is, do you see where ultraviolet bumps up against violet? The V in Viv. And then we have visible light, and then infrared bumps up against red. Okay, so kind of picture all of that. Now, I'm going to kind of show you something. So this is what we call a continuous spectrum. And if my pen worked, I would circle this word right here. This is continuous. Okay, kind of the opposite of continuous, or something in contrast to continuous, is this. What's the difference between a continuous rainbow, continuous visible spectrum, and this? This one's all popped up. This one's all got a line. So for those of you who are into such things, you don't even have to be into it to know that DNA oftentimes is used to trace back to a particular person, right? And this kind of reminds me of the DNA of atoms or even elements. If you know what you're looking at, you can match up those, we're going to call those spectral lines. By the way, this is actually, I think this is the way this works. If you were to go out on a sunny day and to get light from the sun, to break it out into its spectrum, we're like, oh, that's a continuous spectrum. No, it's not. If you have the right kind of equipment actually to magnify it, you would see it has these little spectral lines in it. This is the fingerprint of light coming from our sun. Okay, so these spectral lines are an indication of what is in the sun's atmosphere. It is so awesome. You know, we're never going to set foot on the sun for obvious reasons. Okay, but here on Earth we can get sunlight and we can dissect it, slice it and dice it. And we can do that with, we can look for spectral lines from other stars too. Okay, so it's like a fingerprint. So continuous spectrum, I mentioned fingerprints.
What makes it break up like that?
We're going to talk about that in my slides briefly.
Okay.
It has to do with, for instance, sodium. Okay, what's the symbol for sodium?
Na.
2 letters, Na, very good. Na, sodium. Sodium, and I'll go ahead and kind of give you a precursor to what you're going to see. A sodium atom, what's in the middle of a sodium atom? Starts with letter N. Neutrons in the nucleus. They have 2 N's. Neutrons, particles in the nucleus, that's the N. What else is else is in the center of nucleus atom? Or sodium atom? Protons, yep. Neutrons and protons in the nucleus. All right, so what's outside? Electrons. And actually, it's the electrons that are going to actually be what we call transitioning. So this is a hardcore, okay? This is the protons are actually what makes it a sodium atom in the first place. And neutrons are there to kind of balance the protons. So these electrons can be excited, okay? Let's see, emission, absorption. Okay, as they're excited, as they fall back down, then they hit those lines. And it's just characteristic just of sodium. And actually, I've got some, that's what these are here to show you. That's sodium. What's the symbol for hydrogen? H. What's the symbol for calcium? Ca. Symbol for mercury? Symbol for mercury? It's not an M, it's 2 letters. Hg, mercury. Okay, so we have these lines here that are all about the electrons as they, in this case, actually bounce down to what we call their ground state. Now you might say, well, how'd they get elected? How'd they get excited? Well, here in a minute, when I turn this on, they're going to get excited by just electricity running through that gas that's in these tubes. Another thing, though, before I kind of turn these on, so what color are these lines over here? Purple, I agree. What color are these lines over here? Red. So kind of, that's not an accident. Okay. Literally what we have is the short wavelength. Now instead of nanometers, this A means angstroms, which is a difference of, I think, factor of 10, I'm not sure. Nanometers and angstroms. That sounds right. So this is showing you wavelength from short to long. Okay, so these are, and if you're like me, this would make my head spin, be like a nice little detective thing. What if you had something that had all 4 of these elements? Well, then you collectively see all 4 of those wavelengths, all 4 of those what we call spectral lines. So let's see how we can do it. Now this is going to be kind of noisy, and I think this will turn off. When I say this, I think it's like, okay. So yeah, this is what you guys told me. Atom. In the center of the atom is a nucleus, and within the nucleus we have protons and neutrons. Now, this actually is a hydrogen atom. I know it's a hydrogen atom because it has only one proton, and there's a little electron. So one of these things that we saw was hydrogen, right? I can tell this is a helium atom. How can I tell this is a helium atom? It has 2 protons. Yep, 2 protons. That makes it a helium atom. And with 2 protons, if it's neutral, how many electrons does it have to have? 2. It has to have equal. 2 protons, 2 electrons. Yep. Now, this is the business of why we got those spectral lines. It's really busy, and I wish my pen worked. Maybe it'll work right now. No, it will not. But can you see where, well, I guess they're all falling down. First off, in the center would be the nucleus, and you see these black rings. They're trying to show you what we call energy levels that the electrons can reside at. Energy levels that the electrons can hang out at, energy levels that the electrons can be at. The closer the electrons are to the nucleus, the center, then the less energy it has. So you can kind of see the purple, blue, and red. Which line is longest? I like what your author's done here. Violet. The violet. The violet line is longest. So what that's showing you, actually, if an electron goes clear here from n is equal to 4, okay, n is equal to 4, the electron falls down to its ground state, n is equal to 1, that's what, 3 energy levels? It emits a lot of energy. It's very energetic. It's your brightest spectral line. What about this guy right here? This is just going from an n is equal to 2 to n is equal to 1. So that jump down is less, and it's less energetic. It's the longer wavelength. Okay, and that's all a fingerprint characteristic of hydrogen. So here you can kind of see, if you look kind of from going clockwise, see how these are 2 down arrow ones? This is a down arrow one, this is a down arrow one, showing you exactly what we talked about a minute ago. Okay, these would be a set of spectral lines, this would. Now this one up here, this is an up arrow, okay? So if an electron's going from a low energy to a high energy, it's gonna have to do that by, what I say, sucking in energy, okay? So actually here in a minute, we're gonna see that there are a set of spectral lines where actually instead of giving those bright lines that we saw here, they're dark lines because they're sucking up energy to go to those same characteristic energy levels, okay? And so instead of kind of doing this sort of format, what we usually do is just kind of show the jumps, the electron jumps this way, okay? So these are the electron jumps. And the longer the jump, what happens to the energy? The higher the energy, the longer the jump. The shorter the jump, the lower the energy. That's it. A lot of blah, 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 but that's it. Okay, so how do we get these spectral lines? Well, I told you continuous spectrum was something to highlight, okay? Continuous spectrum means you don't have any lines. This over here, we didn't see this today. This is the sucking out energy. Can you see where it's a continuous spectrum, but kind of superimposed? This is what we saw with the sun a little bit ago. Superimposed on the continuous spectrum are these dark lines that correspond to the jumps that the electrons are making from down to up. They suck energy, okay? And how would that happen? Well, that can happen if you have a continuous source like the sun. If you have a cloud of something interesting, this is the thing you want to analyze, to test for, okay? What will happen, and you're the observer over here, is that this material here will do this material here, the electrons around the atoms here will suck particular wavelengths of energy from its continuous source to make that what we call an absorption spectrum. I know it says dark lines, sometimes called dark line spectrum absorption. If you want to put absorption, you can. I think so. So absorption spectrum. is equal to dark line. All right. Well, how do we get the cool things like this? Well, the way we get the cool things like this is this. Now, can you see the difference between this location and this location? This location, I'm gazing in at the source. I'm seeing the light that's taken out. From this location, I don't have the source behind me. All I'm doing actually is getting to see the cool part where the electrons fall back down from an excited state to a lower state. So you're kind of at a side there. You're seeing what we call the emission lines. Okay? Bright line and emission lines is the same thing. I can't spell emission lines. Bright lines. Exactly. Now, I need to get the test drafted enough so I can give you a solid review sheet on Friday. I will do that. But I promise you that I will ask you something a little bit about these two types of spectral lines. Well, one off is, if I was going to ask you which subatomic particle gives you lines like this, you would tell me, is it the what? I think so. Is it the protons, neutrons, or electrons? It's the electrons. Yes. Yep. Okay, so I guess that kind of ends that part. Switching gears, one last sciencey thing I want to talk about. Okay.
Say that again for the electrons.
It's the electrons changing their energy state that gives us these spectral lines. It's the electrons doing that. Bless them. And it really doesn't have to be that fancy. I mean, halogen gas-filled light bulb, that's how they work, you know? Which the diffraction gratings I gave you, sometimes they're kind of interesting if you just actually look up at the lights, they kind of sometimes use. I don't know if this is good or not. But anyway. Last sciencey thing is this idea, and students usually do pretty good about this. So say something is oozing energy, or a signal, or a sound. Something is oozing energy, okay? That is the thing that's moving. Something emitting, let's say it's emitting a sound, or in this case, radiation, okay? If it's moving towards you, okay, what's going to happen is that its wavelengths are going to be squished. And we call that, let's see, squishing, shortening wavelengths, we call actually that the blue shift, okay? So it's very similar to if you hear the pitch of a car, if a car has got a pitch going on and it's getting closer to you, what happens to the pitch? Does it go up or down when it gets closer to you? It goes up, yes, it ramps up. And so actually it's the wavelengths that are shortening there too. That's the red shift. What happens to the pitch of the vehicle after it passes you? It goes down, it gets lengthened. So as something then leaves you, the observer is stationary, and in this case, as I described now, the observer is stationary and the source is moving. Then as it leaves you, you'll get a red shift. So it kind of goes, usually goes, okay, so this would be the blue shift, red shift. Okay, that's it. So again, here we're kind of tethered to the Earth to try to get as much information as we can from celestial objects. We can actually see stars moving towards us or away from us. We can see galaxies moving towards us or away from us with these shifts. So it looks like this, and this is what I'm trying to tell you. Here actually we have two observers. We have two observers on either side of this train, and of course trains make sounds as they approach their intersections. In this case, the train is stationary. Now the train is going to move from left to right, so what's going to happen to the wavelength to the guy on the right? It's going to get shorter. What's going to happen to the wavelength of the guy on the left? It's going to get longer. Yep. Very good. That's exactly what happened. Yep. This last one then, it's not a train, but it's a light bulb. Now, granted that light bulb would have to be approaching the speed of light, which is a very scary speed for a light bulb to be traveling. But what would happen is this person would visually see it, that white light shifting more blue, and this guy would see it shifting more red. When we talk about black holes, there's for a similar reason? I don't know, maybe so. But when we talk about black holes, there's kind of this similar shift to objects falling through black holes. So this is the way OpenStax approaches this, which I thought was a little confusing. I liked my other two slides, so if you don't like this, that's fine. This is the stationary. S stands for source. We have an observer here. It's not bad, I suppose. You can see the source moving from position 1 to 2 to 3 to 4, moving towards the observer. So what's happening to the wavelength? Getting shorter, yep. And then they added an observer up here. What's happening to the wavelength here? Getting longer. Yep, very good. Now, this guy actually, I wish I could write on this, but this is what we call proper motion. This guy, notice that the motion here is perpendicular. It's sideways. So here's the guy and here's the motion. So he doesn't see any Doppler effect or Doppler shift. Let's see, and he sees no change in the waves and feels left out. I'm like, who comes up with these captions? So anyway. Okay, so this will be due, and we're going to take a look at the telescope slides. So this assignment will be due on Friday. And you can't come to the viewing and not come to class. Although it's very tempting.
Darn.
I know, right?
Just kidding. Wasn't planning on doing
Okay. All right. So what's a photon? I just said it today. A little packet of energy. I love it. It's a little packet of energy. So telescopes can sometimes be called photon buckets because they collect the photons, and I'll kind of show you how that works, and then our eyes get to see it. So, which I like to think that when we're looking through something through a telescope, that the object we're looking at is like, oh, I'm so glad somebody's looking at me. So HST, what does this stand for? The Hubble Space Telescope. And what are these things along the sides here? Kind of like this. Solar panels, yep. Now, this just came to mind that, remember we said that the sun sometimes gets kind of rambunctious. It has more charged particles than others. Actually, the Hubble Space Telescope has a safety mechanism. What's this look like? It's a door, yeah. It can open and close. If the sun is being extra, charged particles being active, it can close its door to save its instruments that are in the back here. So, Hubble Space Telescope. So telescopes, a lot of times when people come to the observatory, and myself even, we think we use a telescope to make things bigger. It's true, and a lot of times people will ask, and I have a hard time doing the math sometimes, what is how many times is your telescope magnifying? I mean, we'll talk about that here in a minute, but not only is it to make things larger, but it's to gather light so things appear brighter and to see detail in objects and, of course, to see things that are far away. So there are two types of telescopes. Okay, there are the ones that use mirrors and the ones that use lenses. Now, for those of you who have looked through that long telescope, how many people think it used mirrors? How many people think it used lenses? It did use lenses, but the one I adopted, I hope to have ready for Friday, it uses mirrors, so then we see both of them. There's too many R's in this whole thing. If you see yourself in the mirror, you see your reflection. So actually the reflector or the reflecting telescopes are the ones that use mirrors. I talked about refraction a little bit ago with the prism. Okay, that's actually what lenses do to concentrate the light. So refracting telescopes are the ones that use lenses. So you guys would probably already intuitively know that a telescope that's got a mirror this big is going to be better than a telescope that has a mirror this big. Yes and no, before we kind of talk about size. The thing is, if the one that's this big it wasn't carefully ground, okay? If the mirror is in poor shape, that sort of things, it might not be as good as this one. So there is that, okay? So, but size does make a difference. So if this is our photon bucket, so for instance, starts with the letter A, what galaxy did we look at the other day?
Andromeda.
Andromeda, yep. So this is M31, and it's actually got a couple of companion galaxies. So now if I increase the mirror, of course I'm going to increase my photon bucket, okay, and I can see a little more detail. Or actually, I think this one says I can see it brighter. Now, the blada blada here says that actually when you increase the diameter, the brightness increases by a factor of a square of the increased diameter size. So that's a big hairy deal. So doubling the diameter will quadruple your light. So revealing detail, I'm gonna turn on my here. So being able to kind of see, we'll never be able to, I would ask this in the form of a question, but I'm gonna go say, no, we cannot see the flag on the moon or anything like that. So we can't see that sort of detail. But again, as you increase the size of the mirror or the lens, then you'll increase the amount of detail you can see. Now, a term I want you to know about detail is up here called angular resolution. Angular resolution. So angular resolution kind of says how fuzzy or how sharp something is. So angular resolution is, can you tell detail here, like this big, that's your angular resolution, or is your detail really, it's kind of fuzzy and you can only tell it here. So the bigger the angular resolution, the poorer the detail you can see. So in general, it says if you double the diameter, you'll double the details that can be seen. So here we've got kind of a comparison again with Andromeda Galaxy. I mentioned kind of the fuzz. This one clearly looks fuzzy. So if we pick on these kind of maybe, I don't know if these are halo stars here, but you can actually see distinct stars here, maybe in this region, whereas you can't here. Okay, so that's, a smaller angular resolution. That's a bigger angular resolution. Here we go. Joke about Orion. So this doesn't do Orion justice. Orion should be rising earlier these days, but the joke we heard this a little bit ago was, we call this Orion's waist, and this is the sword that hangs from his waist, and then he kind of has shoulder, shoulder, knee, knee. That's the way I think of it. So this slide is a little bit out of order. We've been talking about electromagnetic radiation, different cousins. This is visibly what Orion looks like. This is what Orion looks like in X-rays. So does anything pop out at you? Yeah. Again, and it's not that simple. I'm kind of taking a dial and dialing it up from visible to X-rays, more energetic light. But there are things there that we didn't see. Makes you wonder. Well, this is maybe my favorite. This is dialing it down to